thanks for the introduction, and thanks for being here. We are a group of security researchers from Battelle Cyber Innovation Unit. I'm Xing Li, it's Xing Li, Loc Nguyen. Unfortunately, Jim just cannot be here today. So we are very happy to present our tools to support interactive binary analysis. First, we're going to provide you some background of what is interactive binary analysis about. We're going to show you what's the research area, what's the gap between research and the existing security practice. But we'll focus on to show you how to use our tool, including tree and CBAS, to do interactive binary analysis. We use the two demos to show the tool in action for you to understand better. At the end, we'll draw conclusions. Research in the past few years has been focusing on automated binary analysis. And in certain areas, good progress has been made. For example, the automated white box fuzzing, the research represented by a SAGE system, which developed, researched by Microsoft Research and developed as an internal tool in Microsoft, had been credited for finding 1/3 of the vulnerabilities on Windows 7 operating system. So that good progress has been made there. But unfortunately, most of the binary analysis still cannot be automated. So even in the areas that I just mentioned had been automated, not all the problems can be answered. For example, automated white box fuzzing gives you an approach to systematically generate inputs to cover more execution code coverage in order to be able to trigger more vulnerabilities. But it does not guarantee you the vulnerability be triggered. Also, even if a bug or vulnerability be triggered, it does not provide you insight of the exploitability of the vulnerability or how hard to make a working exploit. So all these answers had to be found in an interactive, incremental, iterative approach where the human's experience, expert's skills are the key factors, are the key to the success of binary analysis. So it is our goal to design and develop tools to help you to perform interactive binary analysis. So interactive binary analysis can be applicable to many security areas, such as vulnerability analysis, concurrency analysis, or malware analysis. At this time, our tools mainly draw the result from vulnerability analysis. We believe the tools can help security professionals working on both sides of the vulnerability problem. For people who work on the protection side, either you are a commercial software developer or you are a security analyst working for solutions on finding the vulnerability, we can get you finding it quicker. We can get you to identify the root cause of the vulnerability much faster. For people who are on the other side of the vulnerability problem, such as a pen tester or exploit writer, you can use this tool to refine your exploits, to make it better, more portable, more reliable, and more stable. So in some way, the interactive analysis is like a connecting the dots game. Here, I'm assuming most people have the experience of connecting the dots, or at least know how to connect the dots. So a picture like this, you have a lot of dots. Before you make the right connections, it does not make sense. So binary security analysis, in some way, has similarities as the connecting dots game. But there are significant differences too. First, in the binary security analysis, the dots can move. For example, many people may have the same experience as mine. that you see a problem, you want to look further. You run the same program with the same input, but you don't see the same problem again. So the dots are moving there. And second, compare with a typical connect and dots game. There are a lot of instructions executed, a lot of data created and propagated, even for a short scenario. So there's millions of lines, millions of dots need to connect. Last but not the least, it's not only you need to connect the existing dots, you also need to find the new dots. The dots are not there already. The dots are invisible. And I think that's more important because that's where usually you find surprising results. That's where the vulnerability or unexpected discoveries have been made. So in a way, we design our tools to support all these three challenges. Particularly, our front-end tool, Tsung, will use replay techniques to support fixing the dots. And we use the taint analysis to support connecting the dots. Tsung, together with the CBAS, which is our cross-platform binary automated system, using symbolic execution techniques to help you explore new dots. Before we dive into the details how our approaches work, let's take a quick look about what's the gaps between the existing research and the interactive binary analysis. As I mentioned already, existing research had been focusing on automated analysis for the most part. So it does not directly support interactive analysis. You can see a few things here. There's no practical tools that have integrated the techniques I mentioned earlier, including replay, taint analysis, and symbolic execution. Binary analysis usually works on a trace from different targets, from different platforms or even devices. There's no easy tool or no tool that can uniformly extract the trace from your target. At the heart of the binary analysis, current research usually focuses on one instruction set. There's no unified approaches that can make it very easily ported to a new instruction set. Consider the commonly used mobile system like Android, embedded system, routers, switches. They run non-x86 platform. There's no practical tools for us to easily apply to a different instruction set. So our tools are designed to fill the gaps by using existing techniques available. And particularly, our approach is a dynamic approach. It's a trace-based, but we do the analysis offline. The interactive binary analysis is a new idea for people who are interested in this idea and want to get more details about our research results. You can look for the reference one, which is our paper going to appear soon. For people who want to not already familiar with the popular techniques such as dynamic taint analysis, symbolic execution, trace replay, here are a few references at the end of the talk. So our goal is to make it practical, to make a tool that can be used by the security professionals from the tools that you are already familiar with, merged into your workflow, the daily workflow, without much learning curve. So now, Tsung, our front-end tool, integrated with IDPro, we can port it to another platform if the need arises. Tsung leverages the debugging infrastructure to enable trace collection from different targets, different operating systems. The reason why it works is the debugging infrastructure is supported by most of the modern processors, by the operating systems. So even the real devices such as Android, Cisco router switch, they have the GDB server to enable you to debug it. And our CBus is using a technique called based on the intermediate representation, not directly on the native trace, because the native instruction trace will definitely tie the implementation directly to the particular instruction set. Particularly here, we use the REAL, which is the reverse engineering intermediate representation language from the Binavi tool developed by Zenamix, later purchased by Google, to enable the translation from native instruction and mapping to the intermediate representation. So our CBus is designed to support both automated analysis and interactive analysis. Of course, here, Tree is the interactive analysis application built on CBus, and that's the focus for today's talk. We'll leave the CBus automated analysis application, such as automated further at different occasions. So to summarize, our tools can support fixing the dots, connect the dots, and explore new dots. Let me introduce a running example, a very simple example, just to help you understand the concept, our approaches. So this example started from input from a file. And you might go through some input transformation. And when certain path conditions are met, it might trigger a vulnerable function. But most of the case, it will just behave good. The vulnerable function here contains a buffer overflow, which might be triggered by certain input, but not always happen because the input length should be larger than the local buffer size. So our first task is to help you to fix in the dots. And we have mentioned that many times you see a problem, a behavior, you want to look further. Either it's a crash or the program hangs. You want to look further. So you need to focus on a particular part, or you want to looking at different aspects from a different level of details. But when you try to run the same thing again, it's not exactly as you expect or as you have seen. So why the dots move? What makes the target, your target moving? It's one thing is the multi-threaded issues, as people all know. The concurrency issues bring the non-deterministic behavior. And this is multiplied by the fact the real concurrency by multiple core processors, multiple core, multiple processors in the system. And more interestingly, the security features that are designed to guarantee for protection actually make these things this matters worse. The address space layout randomization is kind of by design to make every time you run the same program, your internal workings are different. Particularly with the fine-grained ASLR built into Windows 8. It almost guarantees nothing will be the same for two runs at different time. So our first, the tree uses the replay approach to record the trace at one runtime for once. Then you can analyze from different aspects many times. So the tree trace will record capture the program states. Actually, we only capture the data, the changes between the program states. That will include the instruction, thread, register, memory, and we have automated this process, so you don't have to do it manually. So based on the debugging infrastructure, we can collect traces from different operating systems, such as Windows, Linux, Mac, and from user mode, kernel mode, And we are still working on to getting the trace from real devices such as Android or the Cisco router switches. People are familiar with the debuggers, use debuggers every day, and might ask the question, say, why in some version of debugger, say GDB 7, already incorporated the record, then replay in a debugger. So what's the difference between us here? I think in general, the high-level answer is this debugger-based replay lets you connect the dots, and tree replay connect the dots for you. What happens in the debugger replay is it can truthfully but mechanically single-step each point in your trace, give you all the facts, and you can select where you want to stop and where you wanted to draw the dots, where you wanted to connect the dots, but it's up to you to do that. I know you can do it. The problem is that only millions of dots there. So Tree doing it differently to ask you to provide the data that you are interested in at the beginning from our GUI. Then you can choose to say what kind of way you want to track. You want to track how the values propagate, or you want to track how your data affect the control flow, the branch points. So you make that choice. Then Tree will automatically propagate the changes along the rules you specified. Then connect the dots so you can move to different dots that is relevant to look further. So we'll explain that with examples here. Let's move to the next point. How do we support you connecting the dots? The approach we are using here is called taint analysis. So first of all, let me point out why connecting dots is so hard. We can generally think the instruction data, they are kind of the dots in this game. In the running examples we show you, it's not that hard because everything fits into one simple file. It's at one place and happens almost one after another. But in the real-world examples, real-world programs, all these basic elements can be complicated. For example, the code size can be big. The inputs it can have plenty and come from all different sources. And the transformation code can be lengthy. The input paths can grow exponentially. Not only they can each of them can be complicated, also they can be separated. Either they are in the code in different modules, or they happen a long time apart. Not to mention that the different runtime, different protection built in make the matters even worse. So the basic techniques we use is dynamic taint analysis. I'm sure many people already familiar with because it's a very popular research techniques. But I think on the other hand, there may be people who not very familiar with that because as I mentioned, these techniques are not integrated with like mainstream security tools such as IDPro. So let's assume that people don't have this deeper background of this technique. Let's start with a few basic definitions. The taint source is kind of the data you want to start with. Taint sink, it's the data you eventually cares. And taint policy is how the taint source might affect the sink. So in a vulnerability context, taint source usually can be your input, the input that the users has control of. The sink could be return address or EIP registers, things like has security implications. A taint policy could be the most commonly used one is like data policies. Your source somehow affects the value of your sink. So taint is taking a data-oriented approach where you look at how the data flow, how the data moves. If you look the other way, focusing on the instruction that transform your data from your source to the sink, usually of our total million instructions executed, you may only have a bunch of the instructions that directly transform your data you are inserted to the data sink you choose. So that sequence of instructions you connect together, that's the key effects I can focus on. That's the slicing we're talking here. So if we use the connecting the dots game to make it easier to see, the starting point is the source, the taint source. And the ending point is the taint sink. You started connecting the dots, and that's the following certain rules. The rule is your policy, your taint policy. And when you finish the connection and it finally makes sense, in this case it's a duck, then that's your slicing. Once you get the duck, you can focus on this to see what's the data there and how it's related to each other and how it's getting to something meaningful. And you can ignore the rest of the dots for now. So back to our running examples. If you see what it's for in this shorter example, we have the taint source. That's the data we read from this instruction, read file. And on the right side, you see the taint graph. We use each node of the taint graph represent a byte. Either it's a memory location or it could be 1 byte in any registers. And we also encoding the registers with thread information, with the sequence information. And we use the different color. The green color represent, usually we use that to represent the taint source. We use red color for the sink. And connecting the data flow and the instructions involved, we get this short taint graph. And that taint graph essentially tells you that the input byte, this particular input byte moves to the first byte of EDX, and then from there it's moved to the memory location, memory stack on the stack. And as a function return, the return instruction pop up that byte to the first byte of the EIP register. So quickly you can grasp the main facts and relations between them. It's not always that easy. As I mentioned, the data dependency, the values is one way, but it's the basic, very common way checked. But the source can also affect the sink in different ways, such as the source might affect the address of your sink, or it might affect your sink by affecting your branch conditions. Essentially, it's affecting what the code executed. That's kind of a control flow tracking. The loop counter, I think, has some potential or a particular interest because that's usually, if you are able to affect the loop counter's value, you in some way either can make it out of bound access or cause thread hunting with a huge number of loops. So connect the different dots following different policies get you different things you want to look further. So next we're going to use a tree to explain how we supported that from the IDA. As I mentioned, it is an IDA plugin. It has 3 main components. The execution tracer responsible to get a trace from different targets. And the taint analyzer process the trace collected from the tracer, then generate the taint graph that describes the key facts of your data, of your instructions involved. And taint visualizer visualize these informations and let you interact with the other parts of the system. Not because it's by design, we use IDA's native graph and the Qt graph. So we kind of seamlessly integrate with the IDA's environment. You usually don't tell the difference between the trace GUI and the IDA's GUI, but that's kind of by design. We do want to point out a few things that we add on top of IDA. For example, the taint graph you have seen earlier. Here it shows the 4 input bytes affect the 4 EIP register bytes. And the taint also can be represented in a tabular format, where we have more added information, such as the starting sequence, the sequence this dots get tainted or is created. What's the sequence when it happened in the original trace? And you may have some taints might be gone, it might be cleaned up or say killed. So that's the end sequence. Usually you can see when the taint is gone. Also, we have the child node. You can click on the child node, then to highlight the entries in the taint table. So it's a different way, but it has a little more information. Also, remember the sequence number I mentioned, that it can trace back to your original trace. Say you have 300, for example, in this case, you have 300 instructions. It will tell you when a particular taint node is created and when the instructions are executed. Plus, it has the detailed information of the state, like registers value, the memory you read or write, and the address, the values. Also, of course, we can represent that in the graph mode, like use IDA's memory view. We can create our own view for stack view, for register view. So the point is, by putting all this GUI together with one GUI, we can show you the comprehensive information you need to dig deeper into the problem. Basically, by click on one particular node, the tree will sync all the information in all this taint table, instruction trace, and the different memory view, register views. One thing to mention is that if you double click on the taint node, it will jump to the static disassembly view of the IDA. So you can statically looking at what the functions this instruction is from, and what's the control flow graph, what's the call graph, who call this function, etc. So all this semantic context, all this big picture help you to tie all these things together. So next, we're going to show you the first demo.
So let's get into our demo. In this demo, we're going to show you how to use our tree IDA Pro plugin to improve your binary analysis capabilities. So in this example, we're going to start with a crash. This crash could have been discovered doing fuzzing, testing, whatever. You have a crash and you want to analyze it. So you can see the Microsoft JIT debugger wants to help you debug this crash. And debugging is a very popular technique to analyze crashes. So you set breakpoints, you step through the code, and you try to figure out what's going on. So you can also use IDA Pro and disassemble the program, walk through it manually. But either techniques you use, they're usually time-consuming and often difficult to do. So we're going to show you our tree plugin and how that's going to make this a little bit easier for the person doing the analysis. So once you have our IDA Pro tree plugin installed, we're going to let's cut off. So after you have it installed, we open the binary in question. So with IDA Pro to analyze it. Sorry, it's cut off, but so just going through the code a little bit, you can see that even though for a simple program that we're going through, it takes a little bit of work to to do the analysis. So for us, we're going to use our tree tracer to generate an execution trace. So we can trace a program from start to finish, but in this case, we could also do it in interactive mode, where you only select the area of interest you're interested in tracing. So you don't have to trace the entire program. So in this example we're going to trace it from the refile functions, because we think it's the input.txt file that caused the crash. So we'll mark our starting point on the refile function. And then we're going to trace it up to all the way to the end of the function, the end of main. So when the program exits, when it's done, we're going to stop tracing. So after we have our starting and ending points, we can run the tracer to generate this execution trace. So hopefully we'll see a crash. All right, so we do have a crash. So we're able to replicate that crash. Now this entire tracing session, the execution tracing session, is stored in a new IDB file. So with that, with the trace in the file, that makes it really convenient and really great for other reverse engineers, analysts to share your finding, your tests, so they can collaborate and try to figure out the problem together. So that's the file that is generated. .idb, trace _ whatever you're programming, named .idb. So next, we're going to use our tree analyzer to analyze this execution trace we just generated. And then we're going to apply the taint analysis techniques that Nathan talked about to solve your problem. So we'll launch our tree analyzer. And for this example, we're going to use the taint data policy. So we're going to track the input as relations to the sink. So in this case, is the crash. So if you run the analysis, you're going to get our GUI layout. So we have the taint graph, we have the taint table, and we have our detailed execution trace, and then the very useful memory information, such as memory view, register view, stack view of that entire execution trace. So one really useful thing that Nathan mentions is that if you double-click on any of the nodes on the graph, it'll take you directly to the IDAPRO disassembly. Now you can apply all your IDAPRO techniques, your disassembly, your reverse engineering techniques to solve your problem. In this case, it takes you directly to the crash. That instruction caused the crash, the function it came from. It's really useful. So now if you compare the two graphs, you have your original IDA graph, which is much bigger, and we're able to make that a much smaller, simpler graph with the tree graph. And so this is a very simple example, but if you're dealing with millions of lines of code and you're trying to figure out, that's a little difficult. Imagine if you do that and use the tree plugin, it can simplify your problem into a much simpler graph. And tree also shows you how the source input directly affect the sync crash. So in this case, the input directly impacted the EIP register. And now, later on, Nathan's going to show you how a CBAS tool can leverage that vulnerability and exploit that.
All right, I will show you how to fix the dots and connect the dots. So the next thing is more important, as I mentioned, that we need to explore new dots. Okay, take a look at the dark thing. I think the key branch point that if you connect the dots 16 here to the 17, that lead to the discovery of the foot of the duck. So in a sense, if you connect it differently, it might lead to something else, such as like this. Well, this is Loc's creation. I don't know what it is, but definitely not a duck. So the point is a program may take a different path, and different paths lead to different behavior. Usually, of course, with some conditions, your input in some way meet the conditions. So in this example, though it's trivial, still with a random input or the input you can try it, probably take many tries if you don't know the internals to trigger the Stack Overflow vulnerable function. So many times, I think people have the experience. You try it many times, and you see it's always the program follow the same path. You wonder, have you tried hard enough, or it's just the path is infeasible? It's not possible. Maybe you need a new way, a better way to answer the question. So tree and CBAS together can help you to answer the questions. So at a high level, the users answer the question through the trace GUI by clicking on a button to say, how can I execute a different path at this particular branch point? Tree will rephrase the question and send it to CBUS. Basically, it's saying, can we negate this path condition? Last time it's a false, take the false branch. Can we take the true branch this time? And CBUS utilizes a technique called symbolic execution. A quick introduction to symbolic execution, just provide a background. Think of the program usually run as the concrete values. Everything is 1, 2, 3, 4, 5, these numbers, and you produce the output as numbers. So everything is concrete, numerical. The technique of symbolic execution is to say some part of the input, you wanted it to be variable, you wanted it not determined. So you make the variable symbol. Then you apply, the program will apply transformations, like mathematical transformation or logical transformation, to generate expressions, symbolic expressions, and you grow the expressions as the program moves along. And at the point, say, you get the path condition represented by symbolic expression and formulas, with sometimes can be many variables and many formulas, but you get a mathematical way to represent the condition with your input. And with the help from a mathematical tool, servers, SAT or MT servers, treated as a black box that can answer these mathematical problems correctly. So in this case, the servers, after servers return, find out that to meet this condition, this byte at this address must be letter B. And tree has the semantics of the program. So it knows that that byte is actually the first byte of your input. So that's how your first branch conditions take the true. It's not that simple in the real case because here we don't do any transformation. In the transformations, you need this kind of mathematical tools to help you scale the reasoning, the problem solving. Later, we're going to show a demo to see what the steps needed to take for tree and CBUS to get your branch conditions solved. But you can see there's quite a few steps involved. So before I dive into the demo, we can show a few things to help you get started. So the goal is here to force the program to take the better path. As you can see, there are 4 key branch conditions. They all need to take true. If you look at the control flow graph here, the normal input will all fall into this false branch, like take all the green edges and fall through. So for this variable function to be triggered, you need to take all these 2 branches, the red edges, and to trigger to find the new path. So we still start with a trace. In this case, we'll offer you different ways to get the trace. Unlike the one in the tree demo, we show you the interactive trace mode. There we use the IDA's debugging breakpoint to get the trace. For the scenarios you are interested, usually it can be short. But here we use a pin. I think many people might already familiar with. It's a popular dynamic binary instrumentation tool that is optimized for you to instrument the program to generate a trace, execution of a trace. So pin is a free software from Intel. The advantage is it's faster. But the downside is it only supports x86. Nonetheless, we have an option to support that if you are familiar, comfortable with pin. By using the GUI, you can have a pin option to trigger the pin tracer we developed. So we developed the pin with the pin tracer. Also, we developed a part called pin agent that is connect the tree GUI with the pin tracer. So the user can specify what kind of the conditions, the command lines, and pass to the pin agent, and then pin agent connect with the tracer to get the trace you like. So after we collected the trace, we choose to do a taint analysis with the taint called branch policy. And that is, we look at how the input will affect the branch points. Here you can see we can get a taint graph that describes all this. The red nodes now here is each one is a branch conditions corresponding to the source code. And by right-click, there's a button on, you can see it in a demo. You can right-click on a branch condition node. Then the tree will generate a query and send it to CBAS. CBAS will generate the constraints describe mathematically of the branch conditions output with the input variables using the process I just described, and get back the results to the tree module. Here it shows a few, the first three branch conditions with the communication between tree and the CBAS. So basically we already figured out what's the bad part, then the fourth will follow. A little bit internal formula look like this. This is a SMT formula, which is the popular servers used, and quite a few of them are available, freely available. You can use. So they have the standard of the SMT format. As long as you generate that, the servers should be able to solve it. And so here, particularly, we're using these three to solve this formula and get the answer back. In the SMT, the server's term is called certifiable input, but it basically tells you what, for this particular input bytes, what's the value should be there. So if we make changes accordingly and run the program again, it will trigger the crash. It means that it took the bad path. So the second part of once you get the crashes, after taint analysis, you can see if the EIPs, for example, in this case, it's the EIP is tainted by the inputs. So as a project writer or people you're interested in exploitability, you can wonder if you can refine the input to, for example, let the program execution jump to the locations you choose, you desired. It could be the entry, maybe a loop sequence you found, or somehow you get a payload in there. It's getting hard today, but it's still possible. For demonstration purpose here, we just put a piece of payload that pop up a message box and say, and show a quick message here. So we designed a simple constraint dialog which allows you to describe what the target you want to constraint on, the operators, and the values you want it to be. And once it's done, click the button, you can send the query to CBAS, and CBAS, basically the same process you have seen for the branch conditions. The only difference here is we're not constraining on a branch condition this time, it's constraining on a particular register's value. And once you get the result back, you basically get the assignment of the input bytes. So let me quickly show you how you can use the tool to really do that. Okay, so here you can see the left side is the tree and the right side on the CBAS. So we begin with trees from a good run. The normal input you get, it exercises the good path. And here we get the branch conditions. By right click on a branch condition, you send the query to CBAS, and you get the results back from CBAS on the right side. So you can do this for the second one. That's the branch. That's the buttons you can click on, and that's the some debug output from the CBAS describing the process of the formula and the results. So basically, you can go through over all this, and you get the right input that get your path, take the path you like to take. And run this, you got a crash. The second part will start from the crash you got, the trace about the crash. The goal is to hijack the execution to jump to the locations you desire. So here you open the trace we collected from pin. And this time we use the data policies because we were concerned about the data dependency, how the input can affect the values. You get a quick Taint graph and use the server, the dialog about the server. You can specify the registers or memories. Choose the operators equal for memory contains makes more sense, and put your values in there. Click on the button, then it will send the query, and the CBus will formalize the formula, then solve it. So next, we just make the changes accordingly and see what happened. So in the real case, it's not as simple as this because usually in the real case you have maybe hundreds of variables and thousands of formulas. Take this the tool to. So as you see that it's the execution jump to the locations we want it to go. So here we already show you with simple running examples to show you the concept and approach and how it works. We did a few user real-world case studies from different platforms, different types of applications, including Windows platform where we have the WMF, ANI, all these classic vulnerabilities. We also have some audio vulnerability. On Windows, we collect some kernel crash, Unix, Linux. Also, we have some work on in progress for a zip application where we're focusing on the compression, decompression activities from Android real device. Okay, so I will just highlight a few facts for the WMF vulnerabilities. For details, you can hope the slides you have a chance to look at after the talk. WMF had been in the news at the time when it was first discovered. There's quite a few ways to trigger this vulnerability from Windows. Almost everything you do will trigger it. So in the sense, we choose one way to trigger this vulnerability with the WMF file we crafted. The particular command line we use is on the top. An interesting fact that we note is between the time the program started reading the file to the time the program crashed, there were 229,000 instructions executed just for the simple scenario. Here's a quick partial Taint graph we collected. This is when the program got an exception from an address that is highlighted here, the red one. Basically, this is 4 bytes. That's on the locations the program trying to execute from, because we have the junk data, so it's a cause exception. We can see this 4 bytes value depend on 4 input bytes. And you see the green node here, and the data policy is the data dependency. So which shows that the input bytes in the original WMF file from the 29th to the 32 bytes affect the value of in these locations. On the other hand, the other dependencies, it's loop dependent on, if you trace back all the way, it will trace back to the input bytes in the original file that correspond to the 7th to the 10th. So which suggests that these 4 bytes get the value somehow from a loop. The counter of the loop is the value depending on the some bytes in the original input file. So what it means, it may not mean totally make sense for now, but it kind of points out the facts, the kind of dependencies you can look at. If you happen to look into the WMF file, you are aware of it, it actually makes more sense, because the 7th to the 10th, the 4 bytes, that's the file size for the WMF file. So say if you have an exploit that you want to work, and you change the, almost certainly you will change the size of our original file. So the file size should be changed accordingly. The other part which affects the value is from the metadata record, where the function, after the functions that trigger the vulnerability, the bytes there is the vulnerability will take the program to execute the memory location. The locations we have seen the exception. So that's the 4 bytes which affect the values of the data dependency value. So also we collected the slicing. We get each individual instructions that are involved in moving the input bytes from the input file all the way to the point that exception happened. It makes sense, make a little bit of sense when you look at individually. It might make more sense if you look at the original context of the program structure, the functions, for example. You know which modules, you know which functions, and you know what's the control flow graph where it's been triggered. And it probably made more sense if you are looking at an even bigger picture, how the program structure in a call graph to kind of fit your knowledge of the program with the details we collected and analyzed. So back to the facts here. Out of the 229 solid instructions, there's only 12 unique instructions are directly involved in the crash that causing the crash. So that's kind of the facts you can focus on first. That's the dots so you can connect first. Okay, so here's the time for conclusion. So based on the interactive binary analysis idea, we designed our tools using popular research techniques such as replay, dynamic taint analysis, and symbolic execution to help you with doing binary analysis interactively. Particularly our tree we implemented on top of IDA, which is the mainstream security tools a lot of people use in their daily work to support interactive analysis. And tree also supports the trace collection, cross-platform, and taint analysis for native instruction taint analysis and replay. We designed CBUS to support both automated and interactive analysis. Of course, here the focus is on interactively doing binary analysis. The key factor, the key feature of CBUS is we perform the analysis of the core algorithms works directly on the IR format, the IR trace offline, by using REAL, the reverse engineer intermediate language, to make it architecture independent. And because REAL already supports ARM MIPS PowerPC as well as x86, so it's much faster for us to use the same algorithm, the same implementation to support binary programs from all these different instruction set. And like any other tools, CBUS and trace are tools to help you become successful. We hope the more intelligence you put into the tool, the more skill you are, the more experience you are, the better help you can get from our tools. And the bottom line is you drive the tools.
So just mentioning a few things, Tree is actually open source. It's available on our Google code page. So you can go ahead and fork it off and shape it into whatever you need. So for instance, you can shape it to be more in line with malware work. So the first version of Tree actually is without the replayer component. That is going to be released at a later date. The CBAS component is also going to be announced with further details. Other than that, if you have any further questions or if you need clarification on the source or the material we've talked about today, or if you want to ask us about any questions about Tree or CBAS, feel free to either email us or meet us out in the hallway.
Yeah, we realize that we run out of time, 5 minutes out of time for questions, so feel free to talk to us offline, and we want to get your feedback. Thanks a lot. A lot of data created and propagated even for a short scenario. So the millions of lines, millions of dots need to connect. Last but not the least, it's not only you need to connect the existing dots, you also need to find the new dots. The dots are not there already. The dots are invisible. And I think that's more important because that's where usually you find surprising results. That's where the vulnerability or unexpected discoveries have been made. So in a way, we design our tools to support all these three challenges. Particularly, our front-end tool, Tree, will use replay techniques to support fixing the dots. And we use the taint analysis to support connecting the dots. Tree, together with the CBAS, which is our cross-platform binary automated system using symbolic-execution techniques to help you explore new dots. Before we dive into the details how our approaches work, let's take a quick look about what's the gaps between the existing research and the interactive binary analysis. As I mentioned already, existing research had been focusing on automated analysis for the most part. So it does not directly support interactive analysis. You can see a few things here. There's no practical. Thanks for the introduction, and thanks for being here. We are a group of security researchers from Battelle Cyber Innovation Unit. I'm Benson Li, this Xing Li, Loc Nguyen. Unfortunately, Jim just cannot be here today. So we are very happy to present our tools to support interactive binary analysis. First, we're going to provide you some background of what is interactive binary analysis about. We're going to show you what's the research area, what's the gap between research and the existing security practice. But we'll focus on to show you how to use our tool, including Tree and CBAS, to do interactive binary analysis. We use the two demos to show the tool in action for you to understand better. At the end, we'll draw conclusions. Research in the past few years has been focusing on automated binary analysis. And in certain areas, good progress has been made. For example, the automated white box fuzzing, the research represented by a SAGE system, which researched by Microsoft Research and developed as an internal tool in Microsoft, had been credited for finding 1/3 of the vulnerabilities on Windows 7 operating system. So that good progress can be made there. But unfortunately, most of the binary analysis still cannot be. Commercial software developer or you are a security analyst working for solutions on finding the vulnerability, we can get you finding it quicker. We can get you to identify the root cause of the vulnerability much faster. For people who are on the other side of the vulnerability problem, such as a pen tester or exploit writer, you can use this tool to refine your exploits, to make it better, more portable, more reliable, and more stable. So in some way, the interactive analysis is like a connecting the dots game. Here, I'm assuming most people have the experience of connecting the dots, or at least know how to connect the dots. So a picture like this, you have a lot of dots. Before you make the right connections, it does not make sense. So binary security analysis, in some way, has similarities as the connecting dots game. But there are significant differences too. First, in the binary security analysis, the dots can move. For example, many people may have the same experience as mine, that you see a problem, you want to look further, you run the same program with the same input, but you don't see the same problem again. So the dots are moving there. And second, compare with a typical connecting dots game, there are a lot of instructions actually automated. So even in the areas that I just mentioned had been automated, not all the problems can be answered. For example, automated white box fuzzing gives you an approach to systematically generate inputs to cover more execution code coverage in order to be able to trigger more vulnerabilities. But it does not guarantee you the vulnerability be triggered. Also, even if a bug or vulnerability be triggered, it does not provide you insight of the exploitability of the vulnerability or how hard to make a working exploit. So all these answers had to be found in an interactive, incremental, iterative approach, where the human's experience, expert's skills are the key factors, are the key to the success of binary analysis. So it is our goal to design and develop tools to help you to perform interactive binary analysis. So interactive binary analysis can be applicable to many security areas, such as vulnerability analysis, concurrency analysis, or malware analysis. At this time, our tools mainly draw the result from vulnerability analysis. We believe the tools can help security professionals working on both sides of the vulnerability problem. For people who work on the protection side, either you are tools that have integrated the techniques I mentioned earlier, including replay, taint analysis, and symbolic execution. Binary analysis usually works on a trace from different targets, from different platforms or even devices. There's no easy tool or no tool that can uniformly extract the trace from your target. At the heart of the binary analysis, current research usually focuses on one instruction set. There's no unified approaches that can make it very easily port to a new instruction set. Consider the commonly used mobile system like Android, embedded system, routers, switches. These run non-x86 platform. There's no practical tools for us to easily apply to a different instruction set. So our tools are designed to fill the gaps by using existing techniques available. And particularly, our approach is a dynamic approach. It's a trace-based, but we do the analysis offline. The interactive binary analysis is a new idea for people who are interested in this idea and want to get more details about our research results. You can look for the reference one, which is our paper going to appear soon. For people who